Hello everyone, welcome back. My name is Masha Pradanovic and we are going to continue our linear algebra review. Specifically, we're going to talk about matrices. So just to remind everyone, our objective in this lecture is to review how to add, subtract, multiply vectors and matrices, create transpose of both of them, and then do various things with both vector and matrices, such as linear combinations. For vectors, we want to calculate inner dot product or dot product, figure out whether two vectors are orthogonal or orthonormal, and use vector norms to compare them. We will also name special types of matrices, and we'll do that both by hand and using MATLAB. So today specifically, we're going to focus on matrices. So in some of these lines, you see matrices outlined in red, and also special types of matrices. Just a reminder, you can refer to chapter 8.1 matrix algebra overview in the textbook. So let's get going. Matrices are arrays of either real or complex numbers, and we're going to use uppercase Roman letters in order to identify them. Now, we will see in MATLAB, and I only hinted at MATLAB during the lecture before, but you will also see that technically vector is a matrix, so formally they're a similar class of objects, and what's the difference is the number of rows versus number of columns. Now, in a general matrix, we're going to have m as in mother, rows, so 1, 2, all the way to m, so my m is number of rows, and n as in Nancy of columns, 1, 2, 3, and all the way columns. So I have a two-dimensional arrangement of numbers into m rows and n columns. And we refer to matrix dimension as m by n. Okay? Now, we can do some standard operations just like you would expect to. If I'm to add two matrices, they should have the same dimension, and then I can simply add corresponding entries in these two matrices. We will typically refer to a number in ith row and jth column as aij. So here A22 is the number in the second row and second column. A21 is in the second row and first column. And you will sometimes, I will write this comma, most of the times I will not, depending whether it's obvious what do I mean by Cij. So for instance, obviously if I'm writing C22, 23, I should separate those two numbers by commas. But if I'm dealing with a small matrix, I will not necessarily have this comma in identifying the element of the matrix. So in any event, I will simply go position by position and add corresponding numbers, subtract corresponding numbers, maybe do a linear combination of them as well. Now, multiplication by a scalar just simply multiplies every element of the matrix by the same scalar. So here, if my scalar is sigma, then every element would be multiplied by the sigma. And finally, matrix transpose simply flips or converts each row into a column and vice versa. So let me actually now do a couple of examples before we move on. I will switch into this writing software of mine, so bear with me until I switch. Alright, so essentially let's say that my matrix A is given as, and let me do an array of numbers, 1, 2, minus 1, 3, 0, and 2. Okay? This matrix has 3 rows and it has 2 columns. Therefore, this is a 3 by 2 matrix. So my M is 3 and N is 2. And if I, for instance, identify this element 3 over here, this is my A22 element, or maybe I can refer to it as A22. Typically, it's going to be obvious whether I'm referring to it with the uppercase or the lowercase number. And my, for instance, element A32 is equal to 2. Okay? So now if I wanted to, for instance, multiply this matrix by a number, I would, let's say, 2A is simply the same matrix but multiplied every element I'm going to multiply by 2. So my result is then 2, 4, minus 2, 6, 0, and 4. Now, if I wanted to keep going, I could, for instance, add another matrix. It has to have the same number of elements. So I'm going to be very lazy and just do 1, 2, 3, 4, 5, 6. Okay. Because the most common matrix out there is just getting the numbers. So in order, I call that a lazy matrix. So when I do this operation, I'm going to add corresponding elements. So 2 plus 1 is 3. 4 plus 2 is 6. Minus 2 plus 3 is 1. 6 and 4 is 10. 0 and 5 is 5. And finally 4 and 6 is 10. Okay? So linear combinations are sort of natural, again, as long as the matrices that in question have the same dimensions. Same number of rows, same number of columns. Finally, the transpose of A is simply a matrix that is going to flip. Rows become columns and columns become rows. Become columns and columns become rows. And we will simply have a transpose as, so what was the first row? It's going to become a first column. So first row was 1, 2. So that's going to be my first column. Then second row was minus 1, minus 3. And that's going to become my second column. And finally, the third row was 0, 2. And that's going to become my third column. Therefore, transpose matrix is now 2 by 3 matrix. So what used to be a 3 by 2 is now 2 by 3 matrix. So this is the transpose operation for matrices. Okay, now I'm going to quickly go back to my presentation. Oops, apologies. So let's continue with a little bit more of theory. So there are some special matrices that I would like to define. Diagonal matrix has zeros for all of the elements except for those where my ID of the row and column is the same. So this is this diagonal. So my element 1, 1 will be non-zero. Then element 2, 2, 3, 3, and so forth to element n, n. And sometimes I will refer to that as diagonal of a row of values. Identity matrix is a special matrix where I have ones on diagonal, only ones. And we will get to multiplication in a bit, but inverse of a matrix is such a matrix A inverse, such that when I multiply two matrices, I'm going to get this identity matrix, however I do it in whichever order. Okay. Symmetric matrix is equal to its transpose. So I'm going to have equal elements, sort of like if I do a mirror image, this is my diagonal, 5, 6, 3 are the diagonal elements. So as I look across that diagonal, I'm going to see the same elements. So my element 2, 1 is the same as element 1, 2. By element 2, 1, I'm referring to the element in second row and first column. Element 1, 2 is the element in the first row and the second column. Okay? So they're equal, and same as 1, 3 and 3, 1 and 3, 2 and 3, 2 and 2, 3. Okay? So now we will actually define how to multiply matrix and a vector. And this is really a special case of matrix multiplication, but it's a simpler case to think about. So we will start with matrix vector multiplication. So let's assume we have a general matrix A, and this is shown, oh, here's my mouse, this is shown right here. So this matrix has m rows and n columns. Then I will need a vector that has specifically n columns, so it's n by 1 vector. Okay. I can proceed with the multiplication because essentially my matrix has the same number of columns as my vectors has rows. Okay. I apologize, I think I said that this has n columns. So I have m by n matrix and n by 1 vector, and I can go and multiply them. Here's how I'm going to go about it. I'm going to take first row of matrix A and do a dot product with this vector x. So I'm going to do a11 times x1 plus a12 times x2 plus, and I'm going to continue until I have elements a1n times xn, and this is symbolically written here. And that's going to give me my element b1, first element of this result, vector b. Then I'm going to just keep doing that. Second row, dot product with my column here, and that's going to give me b2. So b2 is a21 times x1 plus a22 times x2 plus all the way to a2n times xn, and that's equal to b2. Okay. And I'm going to proceed until I have my mth row, last row, and I'm going to do a dot product between that last row and this column here. Let's do an example, and that will conclude our online video. So I already started writing here, so let's say that I have b is equal to ax, and I'm going to give myself an a. Let's also work with 3 by 2 like we had before, so let's say 1, 2, oh, I'm forgetting what the first one was, I'm just going to come up 0, 1, minus 1, 0 as a matrix. I'm going to throw in zeros in there so it's easier to do things for me. So this is matrix that has 3 times 2, so this is my A, has dimension 3 times 2, so now my vector that I can actually multiply this matrix with has to have this 2 times 1, so this has to be a matching dimension. So I'm going to give myself a vector that is 2 by 1, so I'm just gonna go with -1, 3. Okay? So now that I have that, I'm going to proceed with the multiplication. Okay? So I'm gonna do the first element. It's going to be my first row, and dot this product here. So my first element will be 1 times -1 plus 2 times 3. Then my second element is going to be second row, again times column that here, so it's going to be 0 times -1 plus 1 times 3. And finally the third one will be this row here, dot product, the same column. It's going to be -1 times -1 plus 0 times 3. And that gives me a resulting vector, which is equal to, this element here is -1 10 plus 6 is 5. Then 0 plus 3 is 3. And the last one is 1 plus 0. So this is going to give me 5, 3, 1. And this result B is, as I can see, 3 times 1. And basically if I have a matching inner dimension 2, then basically 3 times 1 is my result. So this is matrix times vector multiplication. And this is actually where I'm going to stop. The rest we're going to do or exemplify in class. See you in class.